Imagine walking into the office, you know, to collaborate with this team of just hyper-competent professionals on a massive, complex software project.
Sounds great, honestly.
Right. They are brilliant, but there's a massive catch. Every single morning, they suffer from total amnesia. They just forget everything they learned yesterday.
Oh, wow. Yeah, that would be a nightmare.
Or, honestly, in a scenario that might actually be worse, they remember absolutely everything. But the way they present that memory to you is by handing over a 10,000-page, completely unindexed transcript of every conversation they've ever had.
Just a wall of text.
Exactly. And they expect you to find the one useful takeaway before your morning meeting.
Yeah, that's just total paralysis. I mean, you'd spend your entire day either teaching them the basics from scratch or, just drowning in their raw, unfiltered chat logs.
There'd be zero forward momentum, none.
Right.
And that frustrating, completely unworkable scenario, that is the baseline reality right now when artificial intelligence agents try to work together to solve complex problems. Welcome to today's deep dive.
It's a huge bottleneck in the field.
It really is. So our mission today is to explore this cutting-edge research paper. It's called ConMem, Structured Memory-Guided Adaptation in Training-Free Multi-Agent Systems.
Which is quite the title.
It is, yeah. But the core objective here is to understand how researchers are finally giving AI agents a highly efficient, perfectly organized memory system. And the crucial detail for anyone building or deploying these systems is that they're doing it without having to constantly and expensively retrain the underlying AI models.
Right, which is the holy grail. So to ground us in the architecture we are discussing here, we are looking at large language model multi-agent systems, or MAS.
Okay, so not just ChatGPT in a browser window.
Exactly. In these environments, you aren't just prompting a single monolithic AI. You have a whole team. You might have, say, a specialized coder agent, a reviewer agent running tests, and like a planner agent coordinating the workflow.
And they're passing outputs back and forth to each other.
Yes. But to be effective in a persistent, real-world deployment, they require multi-agent adaptation. They have to learn from past interactions, past successes, and specifically past failures.
Let's unpack the history here a bit, because to really get the brilliant mechanics of this ConMem paper, we kind of have to look at the graveyard of previous attempts to solve AI memory.
Yeah, there's definitely a graveyard.
Researchers didn't just arrive at this elegant solution overnight. They tried a few brute force methods first.
They did. Broadly, the field cycled through 3 distinct methodologies, and, well, they all hit severe bottlenecks. The first is what we call history memory.
Okay, so that relates to the 10,000-page chat log from the intro.
Exactly. The system literally just stores the raw trajectories and past interactions. And when a new task comes in, it just replays that entire massive transcript into the AI's context window.
Which introduces just a massive signal-to-noise ratio problem. I mean, if I'm an AI agent, I don't just see the final optimized code, right?
Right. You see everything.
I see the 5 times the coder agent and the reviewer agent, argued over a syntax error, the dead ends they went down, all that stale context. It seems like that would completely distort the decision-making signal.
It totally does. The AI just gets confused by its own past intermediate arguments. It essentially dilutes the prompt with irrelevant historical context.
Yeah, that makes sense.
So researchers recognized that dumping raw logs was way too noisy, which led to the second iteration. We call that structured or procedural memory.
Okay, how did that work?
Instead of keeping the raw chat logs, the system runs an extraction process. It pulls out isolated skills or procedures from past interactions and just saves those into a database.
Ah, okay. So if raw logs have too much noise, they tried extracting just the pure signal. They summarized the log into discrete skills.
Exactly.
But wait, if I'm thinking about how a multi-agent system actually operates, simply having a database of skills doesn't solve the coordination problem, does it?
Not at all.
If you just retrieve a bunch of skills based on, a cosine similarity search in a vector database, you're really just dumping a pile of uncoordinated procedures into the prompt.
That is the exact failure point of method 2. It relies entirely on the AI's internal reasoning to figure out how to piece those isolated skills together.
It's like handing someone a bunch of tools, but no blueprint.
Right. And more importantly, it doesn't resolve conflicts between them. The AI might pull one skill that says, optimize for memory, and another that says optimize for speed.
And it just stalls out trying to reconcile them.
Yeah, it just freezes. Which brings us to the third attempt, which is the heavy artillery, learning-based memory.
Okay, learning-based.
This is where developers use reinforcement learning to dynamically update the agent's actual neural network weights based on its experiences.
So it actually alters the model itself.
Fundamentally alters it, yes.
Yeah,
It works in the sense that the AI truly learns, but the friction is staggering.
I can imagine.
It requires computationally heavy retraining, gradient updates, or highly curated human supervision. Running back propagation on a massive model every time your multi-agent team learns a new trick. It's just economically and computationally unfeasible for live deployments.
Yeah, if we look at this through an analogy, reinforcement learning isn't just like updating a project file. It's like sending the lead architect back to graduate school for 4 years just to learn how to remodel a specific kitchen.
That is exactly what it's like. It works, but the cost and latency make it absurd.
So this raises the central question of our deep dive today. For you listening, how do we get a perfectly organized, highly actionable filing system for our AI team without having to run expensive gradient updates and retrain the models?
And that is the exact gap ConMem fills. And the way they solved it wasn't by tweaking the neural network. They fundamentally re-engineered the atomic unit of memory itself.
Okay, the atomic unit.
Yeah, they condensed memory into something they call typed and signed strategy cards.
A strategy card. So we're moving away from transcripts and isolated skills and moving toward a highly structured data object. How does the system actually generate one of these cards?
It uses an LLM-driven reflection process. After a multi-agent interaction concludes, the system analyzes the trajectory.
It reviews what just happened.
Right. It identifies the inflection points, the exact moments where a plan succeeded or failed. Then, it synthesizes that specific interaction into a compact card with 4 strict programmatic slots: state, plan, execution, and evaluation.
So it's definitely not just a text summary. The state slot acts as the trigger condition, I assume.
Yes.
It defines the exact environment or problem parameters where this memory actually applies.
Yeah.
Then the plan defines the high-level strategy.
Spot on.
And the execution holds the granular step-by-step actions, while the evaluation records the outcome.
You've got it. That formal structure turns a messy multi-turn experience into a strict, easily readable procedure. But the real power lies in the fact that these cards are signed.
Signed, like mathematical.
Yeah. You have positive cards, which encapsulate reusable, successful strategies. But crucially, you also have negative cards. These are failure-derived warnings.
Oh, a failure memory. So if a coder agent continuously imports a deprecated library and breaks a build over and over, the reflection process generates a negative card,
Exactly.
which essentially acts as a strict programmatic warning, like under these specific state conditions, do not use this library.
And that failure memory is arguably the most valuable asset for multi-agent adaptation. The paper actually outlines a specific mathematical threshold for when a negative card is activated and stored.
Oh, so it doesn't just store every single mistake.
No, it's a risk-reward calculator. The system evaluates the probability of the AI repeating the harmful mistake, multiplies that by the cost of the error, and weighs it against the utility of the action.
Wow.
It even factors in the cost of suppressing a potentially useful step, plus the actual token cost of injecting the memory itself.
So it mathematically proves that remembering what not to do is sometimes far more efficient than trying to force the AI to remember a complex path of what to do.
Yes, exactly.
We learn so much faster by touching a hot stove once and writing a hard rule to never do it again compared to, I don't know, studying 100 days of safe microwave operation.
That's a great way to put it. The card becomes the perfect atomic object. It's computationally lightweight, so it doesn't overwhelm the token budget, but it's structured enough to be instantly actionable by the agent.
Okay, but let me play devil's advocate here for a second.
Go for it.
If I have an ever-growing stack of these highly structured strategy cards, they're bound to contradict each other eventually, right?
Absolutely.
A positive card might say, always use aggressive caching for this database. But a newly generated negative card might say, never use caching when handling this specific secure transaction type.
Right, a direct contradiction.
If a basic retrieval system just feeds both cards to the AI based on keyword relevance, we are right back to the collision problem. The AI hallucinates because it's given conflicting rules. How does ConMem prevent that collision?
This is where the architecture leaps way ahead of standard procedural memory. It doesn't just store these cards in a flat database.
Okay, what does it do?
It links them together, mapping out their dependencies in what the researchers call a typed relation graph.
A typed relation graph. If we were dealing with high-dimensional embedding spaces, why build a complex relation graph at all? Why not just dump these cards into a standard vector database and do a cosine similarity search when a user prompt comes in?
Because a vector database only understands semantic similarity. It does not understand structural or causal dependencies.
Ah, I see.
It doesn't know that card A is a prerequisite for card B, or that card C explicitly forbids card D. By structuring the memory as a graph, essentially a directed acyclic graph, the cards become nodes and the system draws specific types of edges between them.
The paper outlines 4 specific types of edges, actually. Let's break those down.
Sure, so you have positive edges, which are supports and satisfies. These form the procedural backbone.
So if the strategy in card A is a necessary precursor that enables the strategy in card B, the graph draws a supports edge between them.
Exactly.
And what about the control edges, the ones that manage the collisions we were talking about?
Those are constraints and conflicts. A constraints edge dictates that card A limits how card B can be executed under specific conditions.
Okay.
And a conflicts edge is a hard stop. It tells the system that these two strategies are fundamentally incompatible. You cannot deploy both simultaneously.
It operates almost like a detective's causal string board, but highly formalized. You have green strings showing evidence that supports a specific procedural pathway, and red strings highlighting direct contradictions between strategies.
Yes, that visual is perfect.
It maps out the entire logic puzzle of the AI's historical knowledge. But how does the system actually navigate this graph during inference? When you give the AI a brand new task, it can't load the whole board.
No, it uses a mechanism called needs-aware retrieval. Most basic systems just calculate the semantic similarity between the user's prompt and the stored memories.
Right.
ConMem calculates a needs profile. It evaluates the semantic gap between the user's current request, the current state of the multi-agent system, and the specific slots within the strategy cards.
So it's actively asking, where is the agent currently failing?
Yes.
Like, if the agent understands the overall objective, so it has the plan, but it keeps throwing a syntax error during the actual coding phase, the needs profile shifts heavily toward execution.
Exactly. The system will intentionally target cards that have dense information in their execution slots rather than wasting token space on high-level planning cards.
That is so smart.
It retrieves based on the exact type of cognitive support the agent requires in that precise millisecond. It scores the cards based on semantic relatedness, keyword triggers, historical credibility, and that crucial needs alignment.
And then it traces those strings.
Right, it identifies a few highly relevant seed cards, and then it traces those edges to pull in the connected prerequisites and constraints.
Okay, but if I'm listening to this and I build AI tools, my immediate worry right now is latency and context bloat.
Oh, absolutely.
If you pull a seed card and then trace all the supporting green edges and conflicting red edges attached to it, aren't you suddenly holding a massive subgraph of memories? Language models have strict token budgets. If you inject all of that into the prompt, you're going to blow out the context window and slow the system to a crawl.
You are hitting on the most critical and honestly the most aggressive architectural step in the entire ConMem framework: budgeted composition.
Budgeted composition.
Yes. This is the mechanism that ensures latency and context limits are strictly respected. ConMem resolves the conflicts and trims the fat locally, algorithmically, before the prompt is ever injected into the frozen AI agent.
Wait, really? So it happens completely external to the LLM generation step?
Yes, entirely external. When the retrieval system pulls that messy subgraph of connected cards, it passes it to a coordination module. This module acts as a ruthless filter.
A ruthless filter.
Yeah, if two cards are connected by a conflict's edge, the module compares their historical credibility scores and literally drops the weaker card from the payload entirely.
Oh, wow.
It identifies redundant cards and merges them mathematically. It evaluates the constraints' edges against the current environment state. If the condition for a constraint isn't active, that constraint is discarded.
It's acting like a highly protective executive assistant managing a CEO's calendar.
That's a really good analogy.
If two department heads try to book a meeting at the exact same time, the assistant doesn't just forward both calendar invites to the CEO and let them figure it out. The assistant looks at the priorities, cancels the less critical meeting, and presents the CEO with a clean, conflict-free schedule.
Exactly. The AI model never even knows there was a collision.
That's brilliant.
And the performance data on this specific coordination step is remarkable. According to the paper, this module prunes more than 50% of the expanded candidate cards on average.
Half of them.
And when you look at highly complex multi-step planning tasks, it prunes over 80% of the retrieved memories.
Over 80% of the retrieved historical information is thrown out before it ever reaches the prompt. That is a massive reduction in token overhead.
Because 80% of it is redundant, overly generic, or actively conflicting. By aggressively pruning the graph under a strict token budget, using integer linear programming to maximize the credibility score of the final payload without violating constraints, ConMem ensures the AI receives a highly curated, ultra-dense, completely coherent set of instructions.
It essentially acts as an algorithmic bouncer at the door of the prompt, keeping the noise out.
I like that, the bouncer at the prompt.
It's elegant. It saves massive amounts of compute power, it slashes token costs, and it structurally prevents the AI from hallucinating because it is literally impossible for it to be fed contradictory rules.
Exactly.
Okay, so the architecture is clear. We have the trajectory reflection to build the strategy cards, the typed relation graph to map the dependencies, and the budgeted composition module to ruthlessly filter the prompt. But theory is one thing. What happens when this is deployed in an actual runtime environment?
Well, the empirical results validate the architecture beautifully. The researchers tested ConMem using Qwen4b. For context, Qwen4b is a 4 billion parameter model.
That is a relatively compact, lightweight model compared to massive behemoths like GPT-4 or Claude Opus.
Which is a crucial detail. Proving this on a 4 billion parameter model shows that you don't need a massive, hyper-expensive AI to get adaptive, highly intelligent behavior as long as your memory retrieval is structured correctly.
That's the real takeaway here.
And they didn't just test it in vacuum either. They deployed it across 3 entirely different, widely used multi-agent frameworks: Autogen, Camel, and McNet.
And the results.
Across the board, ConMem delivered average improvements of 10.9 to 12.9 absolute percentage points over systems operating without memory. This was tested rigorously across complex coding environments, symbolic planning scenarios, and knowledge-intensive Q&A tasks.
Let's make that concrete for you listening with a specific example from the source material. I was looking at the Trivia QA case study in the paper, and it perfectly illustrates the life cycle of a negative strategy card.
Oh yeah, that is a great example.
In this test, the multi-agent system was given a complex identity-based trivia question. Initially, the system completely failed. Why? Because during its search, it found 2 different historical entities that happened to share the exact same name.
Right.
The AI blindly assumed they were the same person, linked their data together, and confidently output the wrong answer.
A textbook AI hallucination driven by superficial entity matching.
Precisely. But here is the ConMem architecture in action. After the failure, the reflection process analyzed the trajectory, pinpointed the exact moment the agent erroneously linked the names, and generated a negative card. They label it card T1111 in the paper.
Yes, T111.
The execution slot of that failure card contained a newly synthesized rule. Basically, shared names can falsely link entities. Verify the timeline of each entity separately before linking.
Notice that it didn't just memorize the correct answer to that one specific trivia question. Storing the trivia answer would be useless for future adaptation. It synthesized the procedure required to avoid the structural mistake in the future.
Right. So later in the session, a brand new, completely unrelated identity question is prompted. ConMem's retrieval system calculates the needs profile and pulls up that T1111 failure card.
But because of the typed relation graph, it traces the edges.
Yes. It pulls a supporting card, T728, which provides the exact programmatic steps for executing a name link verification. And it traces a constraint edge to pull card T2463, which enforces a strict rule. Identity questions require an exact timeline match.
The coordination module takes those 3 cards, drops any redundant context, and packages them into a concise, conflict-free set of instructions.
So the frozen AI model receives a prompt that essentially says, before you answer this new question, search the 2 entity contexts separately, cross-check the timeline dates, only then accept the answer.
And it works.
The AI follows the injected procedure, navigates around the hallucination trap, and succeeds. What transfers to the new task isn't historical data. It is a brand new, failure-derived procedure.
And that encapsulates the ultimate value proposition of this research. ConMem proves that you do not need to alter the fundamental weights of a neural network to achieve lifelong learning in an AI system.
You just need better memory management.
Exactly. If you structure the historical memory into mathematically signed cards, map their structural dependencies in a relation graph, and aggressively budget what you inject during inference, a static frozen model can become highly dynamic and adaptive.
We have finally figured out how to give that amnesiac team of professionals from our intro a perfectly curated, continuously updating standard operating procedure manual.
Basically, yes.
Every time a member of the team makes a critical mistake, the manual automatically synthesizes a new highlighted rule. And the executive assistant ensures that everyone reads exactly the page they need, exactly when they need it, without bogging them down with the entire history of the company.
It is a paradigm shift for the economics and the scalability of autonomous systems. You achieve the operational benefits of continuous adaptation without the massive compute overhead and deployment latency of reinforcement learning.
It really is incredible. As we wrap up this deep dive, I want to leave you, the listener, with a final architectural thought to ponder. The sheer brilliance of ConMem is its ability to thrive on failure. It turns past mistakes into strict, reusable negative cards that govern future behavior. But this raises a fascinating paradox. If a persistent AI system perfectly distills every single failure it ever experiences into an ever-growing, densely connected web of strict constraints and red strings, what happens when those rigid historical rules eventually collide with the messy, nuanced reality of a brand new, completely unprecedented user request?
It is the ultimate paradox of perfect memory. When does historical optimization become operational rigidity?
Exactly. If you remember every mistake you've ever made and you build an unbreakable programmatic rule to avoid ever making it again, could that perfect memory eventually paralyze the system's ability to improvise?
It's a real concern.
In our quest to solve AI amnesia, are we simply trading it for AI anxiety? Something to think about as you build and interact with these evolving systems. Until next time, keep diving deep.